All right, good morning, everyone. Um, okay, so as a reminder, this Friday, our third exam is going to be posted. So we won't be using class time for it, but it's going to be posted on Friday and then it'll be due um, the next Wednesday at midnight. So we'll have a good amount of time to work on it. Um, And it will be on, so we'll not cover anything that we talked about today. It's going to be all about sequences and series. Today we're talking about, so series still, but a sort of different um, way of using them and thinking about them. So what we're talking about today won't be on the exam. There'll be all sequences and series and a lot of convergence tests, the things we've been talking about for a while. So let's get into it. So here's a very different type of question. So what the conclusion is down below, but we can focus on this question. For which x does this series converge? The series from 0 to infinity of 3 times x minus 2 to the n. So the idea here is that for different x's, you get different series. So for instance, if we pick, say, x equals 0, you get the series 3 times negative 2 raised to the n. And this is a geometric series. The r is negative 2. So this diverges. On the other hand, if you could pick a different x, so say x equals 2.5, then you get the series 3 times 0.5 raised to the n. This is again geometric, but now r is this 0.5, so this converges, and we can figure out what it converges to using the formula for geometric series. So the idea is you have this series with a variable in it, and the question isn't really whether it converges or diverges as just as a series. It's really, we can ask for different x's, does it converge or diverge? And depending on which x you pick, you get different conclusions. But rather than thinking about it for specific x, we'd like to come up with an answer which tells us exactly which x this converges for, instead of looking at them one at a time. So the idea that we can use is noticing if you pick specific x's, you get a geometric series, and then you can decide. Well, what's happening here is that we can say this is a geometric series. The r just happens to have a variable in it. So what we can say is this is a geometric series and it converges whenever the r, the thing being raised to the nth power, has absolute value less than 1. And now rather than being able to say true or false, it converges or diverges, taking the r, which has a variable, and saying that's less than 1, that means we get an inequality telling us which x's would make this r less than 1. And if you have an absolute value less than 1, that means what you're taking the absolute value of is less than 1 and greater than -1. And adding 2 to all 3 parts of this inequality says that x has to be between 1 and 3. And so this answers the question, for which x does this converge? Well, it converges exactly for x's between 1 and 3. And that's what we saw here. 2.5 is in this interval, and it converges, so that matches. 0 is outside this interval, and the series diverges there. And it's also worth pointing out that at these endpoints, if you put in 3, you get 1 to the n, so which is just 1, which means your series is just adding up 3, so that diverges. And if you put in 1, you have -1 to the n, and 3 times -1 to the n, that series diverges because the terms of this series that diverge as a sequence. So we get this inequality, and we don't use the endpoints because those correspond to the absolute value being equal to 1. And in those cases, geometric series don't converge when r is 1 or -1. Questions about what this question is asking or how we come up with this conclusion? So this kind of series is what we're going to start thinking about. Series that have variables in them. So the question isn't just whether they converge or diverge, it's where do they converge? For which x's do you get something that converges? And so these kinds of objects are what are called power series. So in general, a power series centered at A is a series that has this form, a series from 0 to infinity. Cn is the coefficient. So you might have different coefficients for different powers of n, and then x minus a raised to the n. And the idea is that this is like an infinite polynomial. You have some constant term, you have some linear term, you have some quadratic term, you'd have an x cubed term, and so on. And each of these different powers of x minus a can maybe have a different coefficient. We didn't have that in here. So in this case, this is a power series centered at 2, because it's x minus 2. That's the thing being raised to the nth power. But in every case, the coefficient is 3. It's possible that you can have different coefficients which depend on n in some way. A simpler case, which we'll often be thinking about, is power series centered at 0. All that means is that the a here is 0, and so subtracting 0 doesn't actually do anything. So this looks more like the standard form of what might be an infinite polynomial. We have a constant times x, a constant times x squared, a constant times x cubed, and so on. So these are the objects we're going to be thinking about. And the big question is, if you write down a specific one of these, for which x do they converge? So let's try this again. Here's a series. This is a power series centered at 0 because it's just x to the n, rather than x minus something or x plus something. So this is a series from 0 to infinity, x to the n over n factorial. So this is a case where the powers, where different powers have different coefficients. So if you were to write this series out, and let me start typing it up here. This series looks like if you put in 0, anything to the 0 is 1, and 0 factorial is 1 by definition. But this looks like 1 plus x, first power, and 1 divided by 1 factorial. And then we have a half times x squared. So that's 2 factorial times x squared, or x squared divided by 2 factorial. 3 factorial is 1 times 2 times 3, which is 6. And so that is the denominator for x cubed, and then so on. So this is what this series looks like. So we have different coefficients, 1 and 1 and a half and a sixth for the different powers. And we want to know what x's can you put in to make this converge. Now in this case, it's not geometric. In the example that we started with here, it was just something raised to a power. Something without any n's raised to the nth power, and that is geometric. In this case, we have something raised to a power, but also we have this n factorial. So it's not geometric, we need to come up with some other reasoning. And what will often work is the ratio test or root test. In this case, the ratio test is good because we have something raised to a power and a factorial. And for those kinds of series, which are essentially series with a lot of multiplication, the ratio test works really well. So if we try the ratio test on this, we'll end up taking a limit, but what will happen as we get to the end, we'll see that the limit depends on what x is. And so we'll see what we do when we get there. But if we just try the ratio test, thinking x is a variable, okay, I'll still deal with it. I'll deal with that at the end. Let's see what the ratio test says. So the ratio test says take the n plus first term divided by the nth term, take the absolute value, and then take the limit of that. So like the ratio test worked when we didn't have any variables, is take this expression and divide by it. We have that in the bottom. The absolute values, how we can simplify it is we can take the absolute value of x and raise that to the nth power. On the top, we also get to the absolute value of x, but we have n plus 1 as an exponent and n plus 1 factorial on the bottom. And then we, with these fractions, flip the bottom and multiply. So absolute value of x to the n plus 1 divided by n plus 1, and then times the reciprocal of our original denominator, and factorial over absolute value of x to the n. And like usually happens, we look for cancellation. So we pair the x factors and the factorial factors, canceling the exponents, subtracting the exponents, we're left with one factor of the absolute value of x. And in the factorials, n factorial is 1 times 2 times everything up to n. N plus 1 factorial is all the numbers up to n, but then also n plus 1. So we get lots of cancellation. The only thing is this extra n plus 1 in the denominator. And when we get here, we have these two variables, so we have to think about what to do. But the way that we proceed is saying this is the limit as n goes to infinity. So we think that x is not changing. We can think of it as saying if you pick an x ahead of time, this is what the ratio test will give you. And then you take a limit where you only let n grow and x is staying fixed. So no matter what x you pick, if you use the ratio test, you end up needing to evaluate this limit. And if you're holding x fixed, then that's some number, 1 over n plus 1 is going to 0. The top is fixed, the bottom keeps growing, and so that goes to 0. So this limit is 0 no matter what x you pick. So if you pick any x at all, 5, -20, 2 million, if you put those in, you're going to do this work with your x in here, and your limit is going to be 0, no matter what x you happen to start. So what we can conclude is that this power series converges everywhere. So if we want to write that as an interval, it's from -infinity to infinity. No matter what x you pick, if you plug it in, you're going to get a convergence series. Questions about this example? So for these power series, the ratio test and root test and geometric series tests are some good techniques to help us decide whether they converge or not. And I should say right here, the fact that this limit is 0, so the ratio test says you're looking for this limit to be less than 1. And so since it's always 0, it's always less than 1, and that's why it converges. So here we have a series converging everywhere. You could ask, are there power series that don't converge anywhere at all? And a power series, which in general has this form, always at least converges at its center. Because if you let x equals a, what you get is the series, which is Cn times 0 raised to the n, which is just 0. So if you put in a into this series, you have 0 here, 0 raised to the n is 0. Whatever coefficients you have multiplied by 0 is 0. So your series is just adding up 0 a bunch, and that converges to 0. Or sorry, it doesn't converge to 0. The one case is that it converges to the constant term. So this is a little, get rid of this. So the fact that series always converge at their center, if we think about a power series being this infinite polynomial, if you put in x equals a, every one of these x minus a's, a is raised to some power, becomes 0. Multiplied by coefficients, they're still 0. Added up, they're still 0. So if you put in a, then you have whatever your constant term is, corresponding to n equals 0. And then you're adding up a bunch of zeros, so your sum is that constant term. So if you have a power series and you put in the center, it always converges in a kind of dumb way that, except for the first one, every term is 0, so you aren't really adding things up. Right, so the sum is always the constant term. But what can happen is that maybe that's the only point where your power series converge. So if we take this power series n factorial times x to the n, so rather than divided by n factorial, we're multiplying by it. So if we try the ratio test again, the n plus first term over the nth term in absolute values, take the limit of that as n goes to infinity. Rewriting, so doing the algebra, the limit turns into this. Canceling like before, the x's cancel to give us just a single factor of x. There's a single n plus 1 on the top. So this is what our limit is. And if we want to know what happens to this limit, well, it sort of depends on x. If your x is 0, then no matter what n plus 1 you multiply by, that's still 0. And so your limit is 0. But if your x isn't 0, then you have a number times n plus 1, and a sequence that looks like that is going to go to infinity. No matter what you multiply by, if it's not 0, then this limit is going to be infinite. In particular, you have these absolute values on, so even if you put a negative number in, you have some fixed positive number times n plus 1, and that's going to go to infinity. So a power series always at least converges at its center, but in fact, in some cases, it only converges at its center. So these are three really different answers to, here's a power series, when does it converge? And the answers we've gotten are, at one point, the center where it's definitely going to converge. Here's a series where it converges for every number x. And the one we started with was we got a finite interval. And these are actually the only options that there are. Before we get to kind of the general situation, questions about these specific examples. Okay. So in these cases, we're still using the types of tests that we've been using before, but now the fact that there's a variable is going to make us think, the ratio test, we need this limit to be less than 1, and whether it's less than 1 might depend on which x you picked. Okay. So a theorem saying that the situations we've seen are really the only possibilities. So for a series centered at a point A, which has this form, some coefficients times x minus a raised to powers. The possibilities for the question, where does it converge? For which x does this series converge? Which x's can you substitute in to get a convergent number series? The possibilities are it converges only at its center, and we saw that in the third example. It converges everywhere, which was the second example, or there is a number r, so the series converges if this inequality holds. Another way of saying this is that x is within r of the center point A. So that's talking about distance. That's what this inequality is saying. And it diverges if the absolute value of x minus a is greater than r. So this So it says further away from A than R. So you're more than R units away from the center. So it's saying that you have the center and there's some cutoff point where you can look at this picture to see exactly how that's phrased, is you have the center, there's this distance R, you can go in either direction. And if you are closer than R on either side of your center point, you're going to converge. And if you are outside of that, if you are further than R from the center point, you're going to diverge. A small wrinkle that can make things a little more complicated is the endpoints. So this point, which is exactly R bigger than A, or exactly R less than A, those endpoints can go either way. So if you want to know if the power series converges at one of these endpoints, you'd have to explicitly check those points themselves. So this says the examples that we saw are really the possibilities. At only one point, which is the center, everywhere, or you figure out that it converges, or there's some inequality telling you where it converges. And if you turn the inequality around, your series diverges. So since in all cases, the set of points where a power series converges is an interval, that's what we'll call its interval of convergence. Right, so this distance here, this is the interval of convergence. Your interval, you'd have to check explicitly, do you include the endpoints in your interval or not? But your interval of convergence will be symmetric around your point A, although maybe the endpoints might, you might have one converges, the other converges, both or neither. So the endpoints can do whatever, but at least the distance is symmetric around some point A. And this R value, we also think of that as, or we can say that power series have a radius of convergence. Think of this as how far it is from the center to the edge of your interval of convergence. So in this case, or in our cases, case one, where we only had the center, we'll say the radius is 0, because you don't really have an interval at all. Case two, where we had everything converged, we can think of the whole real line as an interval of infinite length. And in case three, the radius of convergence is this R. So at some point, if you find an inequality that says you converge exactly when your distance from A is less than R, that number R you find is going to be your radius of convergence. So this is a lot of terminology, but so the terminology we'll see in some examples. The point of this theorem is just to say, these are the only situations you're going to run into. So to look back at some of the examples we talked about, this first series that we started with, 3 times x minus 2 to the n, we came up with the answer that we did. But along the way, if you go back and look at that work, what we figured out was, well, this is geometric and it converges exactly when x minus 2 is less than 1. So what we can say is that this one right here, because it appears in this inequality telling us exactly when x converges, and if it doesn't happen, the series diverges, that's where we can say the radius of convergence is 1. But then what we did was say, okay, this gives us the radius, but if we solve this inequality, we get that x has to be between 1 and 3. That's where we came up with the interval of convergence from 1 to 3. And in this case, with geometric series, the case where r equals 1, you don't converge. So we know that 1 and 3 aren't going to be included in our interval, because those are the points where if you substitute them in here, you get this is equal to 1. As another way of tying things together, just to kind of confirm that these are the right things, this interval has length 2, from 1 to 3 is 2, and the radius is always half the length of the interval. Right, kind of a radius is half a diameter. That's the relationship here. The whole interval has length 2, and if the center is in the middle, then from the middle to the edge is half the length, which is 1. And so in this terminology, we can also say that this series, x to the n over n factorial, we figured out that this series converged for every real number x. And so we can also say that the radius of convergence is infinite, and the interval of convergence is minus infinity to infinity. These two always go together. For finite intervals, you can have different intervals and different radii, but these infinite ones, these always go together. So let's try one more example with this terminology being the goal. Kind of keeping in mind that we have these situations, you converge at one point, every point, or some finite interval, which is symmetric around your center. So let's try it with this point, or this series. We'll find the radius and interval of convergence for this power series. So because this is just x to the n, as compared to like x minus 2 to the n, this is a series that's centered at 0. So what that means is it at least converges at 0. And if we're in the third case where this interval of convergence is some finite interval, it's going to be symmetric around 0. So what we can say before we even do anything, if the interval of convergence is finite, it's going to look like negative r to r for some r greater than 0. But maybe we'll have to include the endpoints. So intervals of convergence, if they're finite, they're always symmetric around 0, around the center. And if you go r in either direction, you're going to look like negative r up to r. What we'll also have to check if it's finite is, do we actually include these endpoints here? So we'll see what actually happens in this case. This isn't geometric because we have this n here, so it's not just something raised to a power. So you can use the ratio test like we did in our second example, or you can use the root test. I decided to use the root test just to show something a little bit different, and because without the factorial, taking nth roots works out pretty well. So if we try to apply the root test, which means take the absolute value of the terms of our series and take the nth root and see what the limit of that is. If we take the absolute value of the terms of our series, again, we can bring the absolute value onto just the x here, raise that to the nth power, and divide by n. So that is what we're actually going to take the nth root of. When we're here, we can break the root over the top and bottom of the fraction. It cancels the exponent on the top, so we just get the absolute value of x. And we have the nth root of n on the bottom. And this, we mentioned, this limit goes to just 1. So the absolute value of x, it doesn't have any n's on it, so it's not doing anything. It's like a constant. This limit says n is the variable, n is the thing that's changing. If you're not n, you're not moving. So the only thing that happens is the denominator goes to 1, which means we get the absolute value of x. And here we see that the root test says if this limit has absolute value less than 1, your series converges. If this limit has, if your limit is less than 1, your series converges. If your limit is greater than 1, your series diverges. And if it's equal to 1, you don't know. So what we can say is we took this series, we applied the root test, and we figured out that the limit you get is the absolute value of whatever x you pick ahead of time. So what that means is that this only converges if the absolute value of x is less than 1. So that's how, or this is a case where we really see a kind of explicit example that the root test gives you a number, but whether you converge or diverge depends on which x you're actually picking. So since we have this inequality right here, the absolute value of x is less than 1. That's the type of inequality which tells you your radius. So written out, this is saying the absolute value of x minus the center is less than 1. And we know if that absolute value of x minus the center is greater than 1, we know that it diverges. So this number which appears, so the fact that we get this inequality tells us that the radius of convergence is 1. Then if we want to answer the second question, the interval of convergence, we know it goes -1 to 1, but we have to decide if we include the endpoints or not. So we know it's going to look like -1 to 1, But we need to decide, do we have the square brackets? Do we have the the round parentheses? Because we need to decide if we include these endpoints or not. So in the ratio test and root test, what happens is if your limit is equal to 1, then the ratio test and root test can't tell you. And so if the limit is always the absolute value of whatever x you pick, if you picked 1 and -1, you can't use the ratio test or root test, because this says your limit's going to be 1 and you can't make any conclusion from there. So although we know that our radius of convergence is 1, we don't know what happens with the endpoints. So we really need to check what happens for these separately. And what I mean check them separately is actually take the number 1, put it into this series, and then treat it like the numerical series that we've been talking about before today. It's a series that doesn't have any variables. Figure out what it does. And the same thing for -1. We need to put -1 in here. That's a number series. Figure out if that series converges or diverges. So if we do that, if we put 1 into here, then 1 raised to the nth is just 1, no matter what n we pick. So if you put in x equals 1, this series becomes the harmonic series. And we know that this series diverges. If we put in -1 into this series, then we have the alternating harmonic series. And we did this before, but we can do a quick check again. It's alternating, so you should use the alternating series test, which means look at the non-alternating part, just the 1 over n. That's decreasing, the limit is 0, so this series converges by the alternating series test. And that finishes up this problem. So we knew that the interval of convergence was going to look like -1 to 1, but we had to decide which, if any, of the endpoints also are points where this series converges. And by checking them individually, we can see that if you put -1 in, we do get a convergent series. If you put 1 in, you don't. So that means the set of points that you can put into this power series to make it converge is this half open interval. Include -1, go up to 1, but don't include that in. Questions about this example or any of these ideas that we've been talking about? Okay. So we're still using we're still using the test we've been talking about. We used alternating series test, p-test, the root test. We've used the ratio test and the geometric series test. So we're still using all of those. But now the question of converging or diverging isn't just yes or no, it's, well, it depends on which x you pick. And now we want to answer that question. How does it depend on which x you choose? Which x's make this series actually converge? So let's try one of these again. Sorry, I'm just gonna, okay, making sure I remember what we were doing. So let's try one of these again. Find the interval of convergence and radius of convergence of this series here. So there are options for what to do here. You can use the ratio test, or because it's essentially all powers, you can use the root test. Either one will get you where you want to be. I think, but in this case, again, we have some powers of n. So that says maybe the root test will be a little easier. So we take the absolute value of the terms of our series. That's what happens in here with the absolute value of x plus 1. We take the nth root of that. And for looking ahead to some of the simplifying we do, this 4 times n plus 1, I'm going to break that up into 4 times 4 to the n. So multiply these together, that would, to get back, we add the exponents and get here. So broken up like this, we can simplify. Taking the nth root of everything cancels these two nth roots, get absolute value of x plus 1, and then just a 4. When we have the nth root of 4, like in the case of if you have a polynomial in here, if you take the nth root of a fixed number and then take the limit of that as n goes to infinity, you also get 1. So when we take the limit of this 4 doesn't do anything, absolute value of x plus 1 doesn't do anything, this nth root of 4 goes to 1, so we get this expression here. So what this says is, if you pick an x and you take the series you end up with and apply the root test, this is what your limit will be. And so what we can say is that for whatever x you want, the series will converge if this thing is less than 1. So in this case, we have this inequality, but the radius isn't 1. How we find the radius is we need it to be in the absolute values, x plus something or x minus something. So we can get there by multiplying both sides of this inequality by 4, which cancels it over here and makes it show up over here. And this is the inequality that we're looking for. This absolute value of x plus 4, or sorry, absolute value of x plus 1 is less than 4. This is the type of inequality from which you can read off the radius. So this 4 is the reason that we have this 4. We can also think about this if we're trying to talk about the interval of convergence. This interval is centered at -1. So in the way we specified power series, it was x minus something, and that something was the center. So since we are adding something here, that's the same as subtracting -1, and that tells us what our center is. So we know that our radius is 4, but to find the interval, we take this inequality. X plus 1 has to be between 4 and -4. If we subtract 1 from both sides, we get x is between -5 and 3. And this interval matches what we had just said about the center. So we have -1 in the middle. We have 3 over here. We have -5 over here. And this distance is 4 in both directions. So that's the setup for these finite intervals of convergence. There's a center, the radius tells you how far to go in each direction. And so what we know for sure is that if you are between -1, -5, and 3, you converge. If you are outside on either side, you're going to diverge. But what we have to decide is, what about these endpoints? Do you converge at -5 and do you converge at 3? The endpoints are always something that you have to check explicitly. And we'll finish that next time. So power series are the topic that we'll finish out the semester with. We still need to use all of the tools that we've been using so far, or been picking up, but now we're applying them in a very different situation with different questions that we're asking.